Hello everyone, here we will design a prime number detection circuit. For that purpose, first of all, we will obtain the truth table of the circuit. Please note that this circuit is for the 4-bit inputs. So let the inputs be D, C, B, and A, and let's write here the possible input values. These are all the inputs that we can give to the circuit, and here the prime numbers are 3, 5, 7, 11, and 13. Although 2 is also a prime number, but in this example you will consider 2 is not a prime number, so don't take it into consideration here. And for these values of inputs 3, 5, 7, 11, and 12, the output should be 1 here. And for the other cases, for all of the other cases, the output should be, output is F here, as you can see, this is an output, should be 0 for all the other cases. Then I will represent the output in sum of minterms form. F, which is the output, is equal to, here I will use this minterm here, D prime, C prime, and BA, or for this one D prime, C, B prime, and A, plus for this one D prime, C, B, and A, and for this one plus D, C prime, B, and A, and for the last minterm D, C, B prime, A. For those who don't know the representation of minterms, it's a way that we actually express the output. Here, for example, if I give these input values to the inputs, for example, if D is 0 here, C is 0, B is 1, and A is 1, as you can see here, this is D prime, which will be 1, and C prime, which will be 1, and B is also 1, and A is 1, and since all of these are ended here, the output for this part of the expression will be 1 here, and for the other part, since this plus sign is actually refers to OR gate, so if one of the inputs of the OR gate, expressed like this for example, if one of the inputs of the OR gate is 1, so the others are not important here, so other output is 1. So by writing this like this, actually writing this minterm here, I actually guarantee that if the inputs are 0, 0, 1, 1, the output will be 1. Actually the same thing actually available for the other inputs. For example, let's consider the second input combination. As you can see here, D is 0, so D prime will be 1, C is 1 here, B prime, B is 0, B prime is 1, and A is 1, and this is also 1. So when this input combination occurs at the inputs, then this part of the expression will be 1, so the other parts are not important here, the output will be 1. And the same thing for the other minterms expression. So by writing the output and sum of minterms expression, it's called sum of minterms expression, we actually express the output in Boolean algebra. So I can write the output, actually I can draw the circuit by using logic gates after this, writing this expression. For example, writing D, let it be a D input, and D not, this is D prime here, and C and C prime will be here, and B and A, for example, and all of the gates, all of the inputs here are ANDed, and the output of this one are also, all of them will be ORed at the end. But before moving on to that step, I can further simplify this expression in order to use simpler logic diagram, actually use less amount of logic gates. So we will try to simplify this expression before drawing the circuit. We draw here the 4-variable K-map, Carnot map here, and writing the min term values here 0, 1, 2, 3 in this manner, and I will write 1 for the min terms for which the output takes the value 1. Here those values are 3, 5, 7, 11 and 13, and I will group ones like this. For example, this one group, and this is other two, and I can group this one with this one. As I said before, this is not necessary, but just to simplify this expression, if you can write this expression, this is also okay, but this is for further simplification. If you don't know K-map, or if it will be difficult for you to understand the K-map concept, so you can skip this part in your own work. Just you can use this expression. So I will write the expression for the group of ones here, and these are the expressions that I found after the K-map simplification. Then I can write the output as this one. So I will draw my circuits using this expression for the output. So let's do that. I have 4 inputs, B, C, B and A. I will start from this one first. C, B prime, A are ANDed. I need B prime, and for that I use NOT gate. C, B prime and A are ANDed. This is an AND gate here. And after that I will draw this part, C prime, B, A. So for C prime I use NOT gate here. Sorry for that. This is C prime, B and A. Let me use different colors. This is not B, sorry. This is B, and this is A here, and these are again ANDed. And finally D prime, BA, and for D prime I use NOT gate here. This is D prime, and B and A. This is B here, B, and this is A here. Let me take the A input from here, and these are again ANDed. And after all inputs are ORed at the end, and this is output F, and this is our circuit, which is prime number detector. So let's write the Verilog code. Our module name here is prime. Firstly, we will define inputs and output. And then I can write the output by using assign command. Like, as you can see here, this is the same expression as this one. Exactly the same expression here. Another way of writing the code, maybe for example you can call all the gates separately. For example, you can write, and this is an AND gate for example, that is a wire 1 for example, which is the output, wire 1, and the inputs are D prime, C and B, and so on. You can write for the other gates either, and at the end you will write the, for example, let it be wire 2 and this is wire 3 for example, and at the end you will call the OR gate and the output is F and inputs are wire 1, wire 2 and wire 3. But I will not write my code in this way, but you can also try that way either. So let's try to simulate our code by writing test bench. Here my test bench module name is prime tb and inputs are in rec format here, db, c and a, and the output is wire, and I call prime here unit under test and make the necessary connections here, and I will give some different input values in order to check the output. Here firstly I give inputs 0011, which is 3, and after that I'm here giving all the inputs 1, which is in decimal 15, and here I give 0101, which is actually in decimal 5, and after that I give here 0111 and it is equals to 7 in decimal. So let's see that, for example here, first, third and the last inputs, for these inputs the output should be 1, and for the second input combination output should be 0, since 15 is not a prime number. So let's see the simulation results here. As you can see here, between 0 and 10 I have 1 at the output because the input value is 0101, which is actually, as you can see here, firstly I have at the input, actually the order is different here, DBCA, DCB it should be, so this is actually 3, and since 3 is an prime number, the output is 1, and here as you can see between 10 and 20 here all the inputs are 1, as here, so the input is 15 and output should be 0 since it's not a prime number. So as you can see here the output is 0, and so on. By the way, I correct a mistake here in my code. Initially I wrote here plus sign, but plus sign is used for the adding actually. I made that mistake because of the expression here in Boolean expression. So here the plus sign actually in Boolean expression here refers to OR gate. So I should have written here OR gate here. As you can see this sign, initially or when writing my code I wrote here a plus sign, so I see that there is an error, so I correct that mistakes. So you should also correct if you try to simulate this circuit in your computers. So this is important. So here, as you can see, it operates correctly. There is no problem. But I will actually write this code again in another way in order to teach you another method. I thought that you understand this method, so we will try another thing here. Here I will define 4-bit input. I will delete these lines, and I will define 4-bit input, like for example here 30, as you can remember. Input, let it be A, for example, and the output is B. These are default wire type. I will use always block. Always block is used here for example, always means that always, begin, and end. It means that always, this is a sensitivity list, it's called sensitivity list. Always A changes, every time A changes, do the statements written here, and I will write here statements. Again, always when A changes, do the following statements between begin and end. And here I will use another block, which is case. Case, also case, and this is the sensitivity list of case. Case, and this is the end case, end of the case. And it also means that I will explain. I will write a value here, for example 4 bit binary, or I can write actually decimal either. 4-bit binary 0000, and I will write here a statement B is equal to 0, for example. But here I obtain an error here because it says that your output here should be in the register format. So I define my output as register here. After that, as you can see, there is no problem. It actually says that here case, this is a sensitivity list of case, and it says that in case of A is equal to this number, assign B is this number, B is equal to 0. I can write it, for example 4-bit decimal. This is binary 000, 4 bits 0, decimal for example 1. This is the same as 4-bit binary 0001, the same thing. I can write it is decimal and B is equal to 0. This is another way of writing. I can also use decimal here, but for convenience I will write here binary for all of the other numbers. Actually, I'm writing here the truth table here. For this input combination, the output is 0. For this input combination, the output is 0. For this again 0. For this, the output should be 1. I will write this truth table into the Verilog code, but in the case using case statement here. Let me complete it. I write here all the input combinations. In case of A is equal to 4-bit binary 0, output is 0. In case of A is equal to, for example, let's comment on this line. In case of A is equal to 4-bit binary 0011, which is actually 3 in decimal, B is output is 1, and I write
1 for the output. For the input combinations 3, 5, 7, 11 and 13, as you can see here. And I also should modify the test bench. Test bench should have a wire output and registers. Let one input for the test bench, which has 4 bits, and we can here prime unit under test and A connected to A of the test bench, and we can give different numbers here for the input of the test bench. For example, A is equal to 4-bit binary 0000 here, and wait 10 nanoseconds for example, and let's write different inputs, copy paste, and for example let's write here 0 1 0 1, which is 5. This is 0, this is 5. These are comment, by the way, no effect on the code. So let's write here 1 0 1 0, which should be 10 in decimal. And finally, no, here 1 1 0 1 1 0 1. That's finally 13. Let's erase this one. We have 4 different inputs here. First 0, and secondly 5, then 10, then 13. Firstly, output should be 0, then 1, then again 0, then again 1. Let's run the simulation again. As you can see here, this is simulation result, but there is a problem. I want to show you the problem. We forgot to connect the output here. We connect the input, but we forgot to connect the output here. So output is high Z here, not connect anywhere. So let's fix it by just connect B with output B here, and let's run the simulation again. As you can see here, between 0 and 10 the input is 0 and the output is 0, since 0 is not a prime number, and after that input is 5, and since 5 is a prime number the output B is 1, and after that between 20 and 30 the output is A, which is 10 in decimal, but in hexadecimal notation 10 is A, so the output is 0 again, and after 30 nanosecond the output is D, which in hexadecimal, which is 13 in decimal. So since 13 is a prime number, the output is 1. So this code also works properly, there is no problem. So in this video we learn how to write a code for the circuit that we know how it works. For example, we here in this video we try to write a code for the prime number detection circuit. So for that purpose, firstly we form the truth table of the circuit, and after that by analyzing the min terms in the truth table we write the Boolean equation of the circuit here, and after that optionally we obtain the simpler form of the expression here. We also can write here by using this expression our circuit. We can also make this by write our Verilog code by using this expression, but we can also see that we can simplify our expression in order to simplify our circuit actually by using kernel map method here. also we can use the Boolean simplification methods also. But after corner map simplification, we obtain this Boolean equation here, and we draw here our prime number detector circuit. And after that, we by using assign command, assign f is equal to this expression, we write our Verilog code, and we say that we also can write our code in this manner. And finally, we also see that we can write our code by using always block and case statement here, and write the possible input and output values here. And after that, we saw that it's also okay for our purpose.